Hello friend, my name is Ranjit Kumar. Okay, today in this session we will see time domain analysis. Okay, we will discuss about time domain analysis, which is the fourth topic of digital control system. Okay, so first of all, we will see that is analog control system. Okay, this is the analog control system. Okay, we will see what is the natural frequency and damping ratio, that is zeta. Okay, first of all, I have taken as an example like this is error detector. This is gain 1 divided by s square plus s output, which is given by a unity feedback system. Okay, which is controlled by a unity feedback system. So this one is the transfer function. Okay, as you can easily calculate this transfer function like g divided by 1 plus gh. Okay, here g is 1 divided by s square plus s and h is unity feedback, that is 1. So you can directly write it as s divided by 1 plus s, sorry, 1 divided by s square plus s into 1. After solving this you will get same value, that is s plus 1. Okay, this one. Now the characteristics equation will be denominator, just put denominator equals to 0, just put this equals to 0, you will get the characteristics equation, this one. Okay, now from here you can compare with that standard equation, standard second order control system, that is s square plus 2 zeta omega ns plus omega n square, okay, equals to 0. This is the characteristic equation. Okay, this is the standard characteristic equation, and you can compare with this, you will get omega n square, that is omega n, and from here you will get the zeta, that is damping ratio. Okay, so after comparing these two equations, you will get zeta equals to 0.5 and omega n is 1. Okay, now this is the standard time domain equation for control system, that is 1 minus e to the power minus zeta omega nt divided root under 1 minus zeta square sine omega dt plus theta, and you can also write here that is 5. Okay, here omega d is damping frequency, and you can write this damping frequency is omega and root under 1 minus zeta square. Okay, actually this is the bigger term, so that's why we use that is a smaller one, omega d. Okay, now after substituting the value, and theta is tan inverse root under 1 minus zeta square divided by zeta. After substituting the all values, you will get c of t is 1 minus e to the power minus 0.5 t divided root under 0.75 sine this term. Okay, now from this we can easily calculate, that is peak time pi divided by omega n root under 1 minus zeta square, and we know the value omega n is 1 and zeta is 0.5, 0.5, that is means 0.5 square, which is equals to 3.62. After solving this equation you will get 3.62 second. Now this is peak overshoot. This is the standard formula, e to the power minus pi zeta divided root under 1 minus zeta square. After substituting all the values you will get the peak overshoot, that is 0.165, and in percentage you will get the 16.50%. Okay, now at peak time ct max equals to 1 plus mp. Okay, I hope you have seen this type of diagram. Okay, okay, this one is the peak overshoot. Okay, so just this is unity 1 plus whatever mp will come, so just add with this you will get the ct max. Okay, ct max. Okay, that is 1.165 second. Now this is the 1.165 second. Okay, this is the feature, that is sampling has a destabilizing effect. The reduction is sampling time will reduce the peak overshoot. Okay, that is overshoot mp. Okay, after reduction in sampling time. System characteristics equation. Now we will see system characteristics equation. This is the digital control system. Okay, why? Because we have added here, I have added here sampler s. Okay, first of all I have to calculate what is the transfer function, pulse transfer function. So in a digital control system always we have to calculate a pulse transfer function, and in analog control system we have seen that we have to calculate always, that is transfer function, Laplace transform of the output divided by the input. Okay. Now, for this equation, from this equation, we can say that is system characteristic equation will be 1 plus gh of z. Okay. Now this is our system characteristic equation. This one is system characteristic equation after substituting after putting equals to 0. Okay. Now the root of this equation will give our the root of the characteristic equation, that is nothing but the poles of the closed loop transfer function. Why closed loop transfer function? Because this is the first transfer function of this whole closed loop control system. Okay. No. No. Effect of the closed loop jet plane poles on the system transient response. Okay. Now the standard S plane second order transfer function. This is the second order standard second order transfer function. That is omega n square s square plus 2 zeta omega n s plus omega n square. I told you earlier. I have told you that is this one is a characteristic equation of the standard second order transfer function, second order system, where omega n is undamped natural frequency and zeta is the damping ratio. Okay. And this one is the characteristic equation. Already we have I have discussed about these things. Now poles will be poles means just substitute equals to 0 and whatever value of s will come, that is our poles. So these two value will be the poles. Okay. These are the poles. Now for equivalent S plane, what we have to do, just substitute instead of what I can say, like z equals to, just put z equals to e to the power st, and from here you can calculate that is value of s. Okay. Now otherwise you can s is already calculated, so substitute the value of s here, you will get z value. Oh, in z plane we have to see the constant value in terms of z. Okay. Now this is the equation after substituting all the values of s, that is both values, uh, both value s1, you can say this one is s1 and s2, you will get uh, that is e to the power minus zeta omega n t, e to the power plus minus zeta omega n t root under 1 minus zeta square. Just we did nothing, just to substitute this value. Okay, these two value here. Now we can say this term is r. Okay, and this term is whole term is theta, because of plus minus, just I have added here, this one is theta. Okay, this term plus minus j theta. Okay, exponential is nothing, means so for angle I am taking only this part as a theta. Okay, and you can write it as like a sine theta plus minus j cos theta. Okay, again you will see the value of theta. Okay, now from this we can say that is r equals to this after taking log base e. So what will happen? What will become? Log r equals to minus zeta omega n t, because of log base e to the power anything x, which is equals to x. Okay. Now after solving this equation, so that is zeta omega n t, and minus side is just transposing this side, so it will become like this. Let's say this is equation 1. Also theta equals to this part, this one, theta equals to this one, omega nt root under 1 minus zeta square. That one I have written here. Okay. So omega nt root under 1 minus zeta square, that is theta. Now these two equation become. Okay. So what I have to do, taking the ratio of these two equation, just divide 1 by 2. Okay. What will come? Zeta omega nt divided by omega nt root under 1 minus zeta square equals to minus log base er divided by theta. After solving these equation, you will get that is zeta. Okay, zeta equals to minus log e base r divided by root under log base r whole square plus theta square. Okay, this is the standard equation. Okay, you have to memorize these things. else you can calculate. Now, and zeta omega nt, and from here we can calculate that is omega n, undamped natural frequency. That is 1 by t root under log e base r whole square plus theta square. Okay, this one is another important formulas. Now, the time constant, which is denoted by tau, is given by tau equals to 1 by zeta omega nt. Okay, we studied in control system that tau is 1 by zeta omega nt. After substituting the all values, we will get that is tau equals to minus t divided by log r by c. Okay, and from here we can calculate that is value of r. Okay, so this one is the r, and you can say this is the means this is the equation of circle also. Okay, no, I have taken one examples. We will solve this example and we will calculate the value of zeta omega n and tau. Okay, so first of all we have to calculate the pulse transfer function. So from this block diagram we can easily calculate pulse transfer function. Like first of all we have to calculate here two gain is given. Let's suppose this is gain of volt circuit and this one is gain of plant. Okay, we can say. So we have to multiply these two equations. After that it is passed by, which is passed by the sampler having sampling period is 1 second. Okay, so after calculating means first Z means zero order volt circuit. What is the transfer function of this? So that is 1 minus e to the power minus st divided by s. Okay, into this term I have written here. Okay, and zero order volt equation is I have calculated in lecture first session. You can see there that is e minus st divided by s. Okay, this is zero order volt equation. Okay, now after applying partial fraction method we will get like this. Okay, after partial fraction method we can write this as a divided by s square plus b divided by s plus c divided by s plus 1, and just find out the value of a b c. You will get 1 by s square minus 1 by s plus 1 by s square. Okay, now after taking z transform, this equation will become, this term will become 1 minus z to the power minus 1, and this is the ramp function. So tz divided by z minus 1 whole square, and minus 1 by s, that is this is unit step function. And what is the unit z transform of unit step function? That is z divided by z minus 1, and same, but it is shifted by e to the power minus t. After substituting the value of t, that is 1 second, substitute the value of t equals to 1 second, then we will get this equation. Okay, and you can calculate with the help of calculator, you will get this equation. Okay, now from here what will be the characteristic equation? This part will be the characteristics equation. Okay, z square minus z equals to plus 0.362 equals to 0, and from here we can calculate z poles, that is poles. Okay, so poles will become like this. Okay, and we can write in angular form, rectangular. This is rectangular form, this one is rectangular form, and in polar form that is r at an angle of plus minus omega nt root under 1 minus zeta square, or we can say like this. Okay, so from here we can compare these two equations. So we will get r equals to 0.795. Okay, and theta is omega t root under 1 minus zeta square, which is 0.89, this part. Okay, now so we know that the formula of zeta, this one is the formula is I have calculated here, as you can see. Okay, this one I told you this is very, very important. Okay, now after writing the formula, just substitute the all values. Okay, you will substitute all value, you will get the value of zeta, that is 0.249. Also omega n equals to 1 by t root under this is the formula. Just substitute the value in the formula. Okay, you will get that is omega n, and tau minus t divided by log e base r equals to this. Okay, and after substituting means calculating the value of log is 0.795, that is minus, that minus will get plus, and the value will be 4.358. Okay, so the from this way you can calculate omega n, tau, and one more factor, that is damping ratio. Okay, now we will talk about a steady state error. Okay, steady state error, in after this, after time domain analysis, we will discuss about a steady state error. Okay, in the steady state error, first of all, this is the control system, that is analog control system. And we know that in the analog control system, that is steady state, limit t tends to infinity e of t. And after converting this e of t in s domain, so as you know that we have to multiply it with s, and it will become e of s. Okay, simple. And s tends to 0, that is, you can say final value theorem also. Sorry, initial value theorem. Okay, this is initial value theorem. Why? Because from this way we have to calculate s tends to 0. Now limit s tends to 0 s, and error function, error transfer function, from here you can calculate it easily, that is r of s divided 1 plus g of s h of s. Now this one is for analog control system. Now for digital control system, just apply one sampler, that is s. Okay, after applying sampler, we will see what is the pulse transfer function, and after pulse transfer function we will see what is the changes in steady state error. So the steady state error of the above digital control system, okay, at you can say any sampling state, that is t, is defined by e star equals to limit t tends to infinity e star of t. Okay, so we just substitute, replace t with n of t, that is time sampling instant t, sampling instant t, just replace with t, so it will become e of nt. Now applying final value theorem, so in after applying final value theorem, what will happen? Here we will see that is e star of ss equals to limit z tends to 1 and z minus 1 e of z. Okay, I have discussed this part in second lecture. Okay, from there you can find out, okay, how we are applying these formulas. Okay, now that one is open loop transfer function, this one is open loop transfer function, where, okay, I didn't calculate it. Okay, yeah, this one is, wait, yeah, this one is closed loop transfer function, pulse transfer function, closed loop pulse transfer function. This one is closed loop pulse transfer function. Okay, like this way we can write. Okay, now a g of z equals to z transform of gh of s gp of s. Means first of all we have to calculate g of z. So g of z means whole gain from here to here, this whole gain, that is zero order hold and plant. Okay, so this one I have written. Okay, after taking z transform, like, means first of all it was like this, zero order hold into that plant. Okay, after taking z transform, so it will become g of z, and we have to, we can write z transform of that zero order hold into plant. Okay, after that we have to calculate the z transform of this function. Okay, so directly we can write like this. Okay, z transform, we have to calculate z transform of gp of g plant of s divided by s. So from here, gh of z equals to 1 minus z is same, this is this will become same, and gp of s, that is gp of s h of s. Okay, why h of s? Because here I have taken, means not unity feedback, this is some transfer, having some transfer function, that is h of s. So that's why I have taken here gp of s h of s divided by s. From figure system, error e of t is defined, and how we can define, that is always I told you, okay, in digital control system always we will see in terms of z transfer function. Okay, so this is time domain, so after taking z transform, e of z equals to z transform of e of t. E of t is error, means that is error signal. Okay, now also c of s, this is the, means calculation that I have discussed in lecture 1. Okay, in lecture 1 you can find out how we calculated this value. Okay. Okay, so from here, after taking z transform, so star function will directly become u of z, which is equals to r of z divided by 1 plus gh of z. Okay, now steady state error in z domain. So how we can write? As I told you, that is steady state error limit z tends to 1 z minus 1 e of z. E of z I have calculated here. Just substitute the value. You will get limit z tends to 1 z minus 1 r of z divided by 1 plus gh of z. Now now means further from here we will see different at the different input when we will give the different input, that is r of z. So how the error steady state error will changes. Okay, so first of all, in discrete error constant, we can say that is step input. For a unit step input r of t, as we know that r of t is u of t at t greater than equals to 0. This one is r of t. Okay, this one is r of t. Okay, after giving some sampler, after giving some sampler, so it will become like okay, at every instant, that is t 2t 3t, like this way. Okay, and taking z transform of this r of t, so we will get r of z equals to 1 by 1 minus z. A simple, you can say z divided by 1 z minus 1. Just substitute this r of z here in this formula, so it will become a steady state like this. Just substitute the value, this part will cancel out, so it will become like 1 divided by means after substituting r of z, and after that just applying z tends to 1. Okay, whenever you will apply z tends to 1, that is limit z tends to 1, z divided by 1 plus gh of z. So this z will become 1, this one is constant, plus here means we don't know what is the h of z, so that's why applying this limit z tends to 1 gh of z. Okay, so we can say this part as some constant value, that is kp, which is nothing but discrete error constant, this one. Okay, discrete error constant, that is kp. Okay, ess only. ess star of s equals to 1 by 1 plus kp, where kp is this formula. Just write this equation. And discrete position error constant. Why position? Because of this is discrete position error constant. Now first one is complete, that is study means step input. Now this is for this is means after that we will talk about ramp input. In ramp input, everyone knows that r of t is tu of t, this one. And after taking sampler, so it will become like this after taking sample. Okay, so we have to calculate the z transform of this function. So we directly write down z transform r of z equals to zt divided by z minus 1 whole square. The steady state error, same formula we will apply here. Z of t, just substitute the value of r of z. After calculating, we will see here t divided by limit z tends to 1, z minus 1, 1 z minus 1 term will be remains here. So that's why we multiply here. After that, substituting that z tends to 1, so it will become that is 1 by kv. Just means I am replacing this, assuming this part as a kv, that is discrete ramp error constant. Okay, kv is discrete ramp error function, which is nothing but 1 by t limit z tends to 1, z minus 1 gh of z. Okay, after that third one is parabolic input. In parabolic input, t square by 2, why we are taking 2? Because of whenever we will take the Laplace transform, z transform, that constant 2 will be multiplied, so this 2 will be neglected, so it will become 1. Okay, that's why we multiply here 1 by 2. Okay, so some constant parabolic equation like this. Okay, after sampling, so we will get like okay, so again substitute the value of r of z, we will get this function. Okay, and 1 by ka, we denote this as a ka, where ka is this, and which is a discrete parabolic error constant. Okay, now this means one question I have taken to calculating the different means steady state error, how we can calculate steady state error. After that, these constant value, that is kp, kv, and ka. Okay, so compute the error constant and relate them to steady state error. Okay, relate them means we have to find out the steady state error. So as we know that kp is limit z tends to 1 gh of z. Just substitute the value and put the value z equals to 1, and we will get the, that is infinity. It means steady state error will be 0. 1 by 1 plus infinity, that is 1 by infinity, which is 0. And for position error, velocity error constant kv, it will become 2.59 divided by t. And for acceleration error constant, and what we have, discrete parabolic error constant. So discrete parabolic error constant will become a ka equals to 0. Why 0? Because whenever you substitute z equals to -1, oh, sorry, 1, so 1 minus 1, 0. Oh, no, this part will cancel, but one term z minus 1 will remain. So 1 minus 1, 0, so whole term will be equals to 0, and steady state error will become 1 by ka, that is infinity. Okay, that one is first type of question. This is second type question. And from here, that is, let's say this is sampler, and here also we have let's say s1, s2. Okay, and from this type of block diagram will be given, and from this you have to directly calculate, that is kp, kv, ka. So from here, this diagram, you directly calculate limit z tends to 1 g of z h of z. Why g of z h of z? Because two sampler applying here, and just follow the, what I can say, follow the closed loop from means starting from here. So one sampler is applying, so for sampler always write like this, gs, so star. Why? Because of sampler. After that again sampler, so again we have to take one bracket. So after that, what is written here? H of s. Just write h of s. What is here? We have to take star. Why? Because one sampler is applying. If again one star is here, when one sampler is here and some function here, again we have to take like this and write that function and like this. Okay, just find the closed loops, means transfer function like this way. That is very easiest method. Okay, to calculate the transfer function, means first transfer. After taking z transform, so I told you star function star will become again a star, and it will become h of star. After taking z transform, so it will become g of s, g of z, h of z. Okay, understood? So that's why I'm taking here g of z, h of z. Now after that, kv 1 by t limit t tends z tends to 1, z minus 1. Why z minus 1 term is taking here? Because 1 z minus 1 will be cancelled out. Okay, so that's why I'm writing here. Means I have written these things. Now ka 1 by t square, or that is z minus 1 whole square. Why two term is coming here? Because the one term will be cancelled. Actually from here three term will be there. Here three term, like z minus 1 to the power 3, and this function will become 1 by z minus 1, and after that you write this g of z, h of z. This one term will cancel, that is. Okay, now from this way you can calculate. Again here one more block diagram is given, and from this you can calculate kp, kv, k. Okay, directly first of all you have to calculate the transfer function. How will you can find out transfer function? I start from here. One means sampler is given, just give the bracket g1 of s, g1 of s. Okay, so we have to take sampler. Why? Because sampling. After that again one bracket we have to take g2 of s. Okay, write on g2 of s. Okay, just go, no sampler in between this, so that's why we have to multiply these things. Okay, after that completing bracket and just apply starting. So g1 of s, g star of s, g2 g h of s. Okay, so we have to first of all write in single function. Why? because in whole function star is given. Okay, so that's why first of all we have to make g to h of s. Okay, here is star, and after that g to h of z means h of s. After z transform g to hz. Understood? I have written here G12, and from that way you can calculate. Now, again for this equation, for this block diagram, you can again apply like same closed loop, follow the closed loop function. So just start from here. One transfer means one sample is given. After that, G1 of S. Just give the start. Now again go further. Again one sampler is given. So give bracket and write down G2 of S. Just go ahead here sample. So we have to first of all complete this part. Now after that again go here again one more sampler is coming. So for that we have to take again another, and after that write h of s. Is there any function? No any function. If here let's suppose here p of s is given, we have to write here p of s. Then after that taking bracket. Okay, but no p of s is here, so no need to take. Okay, like this. After that taking z transfer function, directly you will get these two functions, that is g1 of z, g2 of z, h of z. Okay, and this one the function. Okay, from this way you can calculate the steady state constant, steady state error. Okay, and time domain analysis I have discussed, and from that time domain analysis you can calculate natural frequency, that is omega n, undamped natural frequency, and damping ratio, that is zeta. Okay, so just go through this, you will get the ideas regarding how we can calculate all the values. Okay, this is the time domain analysis. Okay, now for this lecture, I will attach the PDF of this lecture in description box. You can find out from there. Okay, thank you. Bye bye.